Hi everybody, thanks for coming. Sorry for the technical delays. But here we go. So I would like to talk to you today about generative and declarative programming, which are relatively well-known techniques, so to speak, in the expert community, but perhaps somewhat novel to other parts of the C++ community. And the thing is, in this conference, which hasn't been going too long yet, but most of you probably have seen one or two fancy C++ 17, maybe C++ 20 features even. And intuitively, sometimes it's very clear to see, we had this super complicated code before, and now structured bindings and fold expressions make this really easy to work with. But I think we as a community sometimes have a problem articulating to other people what actual problems we can solve with these new language features. And my talk is a kind of constructive attempt to try to fill this gap by not just showing you C++ 17 features in the wild, but by actually showing you what kind of problems we can solve with them. So before we do that, who am I actually? What kind of background do I have? I'm a freelance software developer from Berlin, or rather working in Berlin currently, on embedded systems and things like that. I like to combine type safety with low-level software, so operating systems, compilers, firmwares for embedded systems. And the thing that fascinates me about C++ is that even when we work on this very low level, like hardware interfaces and poking external hardware registers, we can always build very useful abstractions on top of it regardless that improve the readability of our code or just the general correctness guarantees and ensure that our software in the end works better than when we wouldn't be using these kind of abstractions. I try to use this whenever I can, but most prominently I've been doing so in game console emulation, which I've been working on for, close to 10 years by now. Kind of just stuck around, never really left the community. Some projects I worked on were PPSSPP, Dolphin, and Citra, which are PSP, GameCube, Wii, and 3DS emulators respectively. So especially Dolphin, if you've ever tried to emulate the GameCube or the Wii on PC, you probably have heard about that project. Yeah, most of the stuff I do is public. You can look up the source code on GitHub, and you can follow me on Twitter if you like. That's usually where I post about emulation findings, and also about nice C++ memes like fun stuff you can do with zero-width white space in class names. That's it. What is this talk actually about? As I was saying, it's about emulation, of course, specifically about serialization and emulation, which sounds kind of plain maybe, but it turns out serialization is actually a very critical component of every emulator, as I'll show in a minute. And a specific subsystem we'll look at is interprocess communication of an operating system emulator. And we will try to solve a given problem using a declarative and generative approach. And the question here that I would like to answer to you is, how can modern C++ help? How can it help reduce boilerplate? How can we make sure that the programmer only needs to write down how can we make sure that they only write down what's necessary for the compiler to figure everything out and have the compiler figure out all the boilerplate? And how can we figure out how to do compile time verification of certain properties so that instead of having asserts fire at runtime, the program that is not correct will actually just not compile in the first place? And finally, how can we maximize reuse by centralizing our definitions in a central place and just reusing that single component in every different subsystem later? Right, and to do so, let's just look at a kind of structural component overview of a game, for starters. What you can see here is that there is so various different CPU side modules. There might be a main thread that controls rendering operations and things like that. And there might be some sort of scripting engine. There's an operating system on the system. And of course, some sort of GPU. And now we can consider how do these components actually interact with each other? And considering the main thread and the scripting engine, from the programmer side, it's really trivial. The main thread tries to call a function from the scripting engine, well, it just does that. It's a C++ function call. It's trivial. When they try to interact with the operating system by using system calls, for instance, it's slightly more involved because you need to make sure that you use the correct calling convention, so put the registers in the right order and things like that. But that's kind of taken care of by the compiler, so that's easy too. And the most complicated case is when you try to interact with the GPU or the GPU driver. You need to send binary data to the GPU, for instance, so like vertex data or state updates. But at the end of the day, that's not a function call, but just a mem copy around, so that's really simple as well. But if you try to look at it from the lens of an emulator, things get complicated. So sure, on the left side we have the virtualized CPU, so all the CPU side threads kind of get melded together and we don't really have to worry about anything that happened there. But let's say the CPU tried to interact with the virtualized GPU to do some sort of rendering operation maybe. Well, what the emulator sees in that case is just main memory basically in the center, just a bunch of zeros and ones that we don't really know any structure about. And the CPU will write its raw data just into there and will just keep doing, and at some point it will trigger that GPU side operation. And at that point, we need to make sense out of this untyped sea of raw data. So if there's vertex data in there, we need to identify floating point positions, integer colors, or if there's a stat update, we need to kind of map the bits and bytes down to enums and structures. And that's a non-trivial task to do. And in the end, that's a de-serialization problem. A de-serialization problem that is critical because we don't want to have our GPU core operate on raw bits and bytes. We want to have it operate on something that looks remotely similar to C++ code. And a similar issue occurs with the virtualized OS. So if we consider a system call on ARM32, for instance, which is the architecture used on the Nintendo 3DS, we see that a game might just write a bunch of values into registers R0, R1, R2, etc. And then it will trigger a system call operation with the SVC instruction. And at that point, usually the register data gets sent to the operating system, and then some sort of operation is completed. But what we would like to do in the emulator instead is to have some sort of well-typed function call that we just invoke in that scenario. So we want to have a function, SVC start DMA, that actually takes well-typed data, because otherwise we kind of just have this, these values and can't really make sense out of them. So that's actually a non-trivial task though, because well, we don't have that type information around. It's just those values, and we need to convert, for instance, this value 5 here to a lookup handle, because we might have some sort of strong typed objects in the operating system. And usually you'd also expect that these values are just sent over in strict order, but actually what the operating system on the 3DS does, it kind of reorders them. So in this case, the first argument for the system call is read from R1, then from R2, then from R3, right? And then it jumps back to R0, just because they like to mess with us, and then it jumps back to R4. So that's all the kind of stuff that we would need to manually take care of if we wanted to translate these values into a proper C++ function call, which we want to do. So maybe this gives you a kind of idea of what kind of problem we're tackling here. This is something I talked about at a C++ London meetup before, so if you want to learn more about that, check that out. There's a recording available online. There are a number of other scenarios where this problem occurs in emulation, so system calls is one of them. But also the Interprocess Communication subsystem that I'll illustrate in a minute. There is emulated file I/O, where we might have some sort of file on disk, maybe a bitmap, for instance. And the bitmap usually has some sort of file header at the top that tells us like what's the width and the height and the bit, the number of bits per pixel in the pixel and the image. And you want to basically read that kind of header into a C++ structure so that you can just conveniently read the width and height rather than referring to offsets within that file. And in emulation, that problem gets slightly more interesting, actually, because, well, maybe the endianness of your file, of your emulated system, doesn't match the host. And then you need to actually iterate over each member in that file header and byte swap it around so that you get reasonable values out of it. Right, and finally, there's GPU command buffers, which is similar to the interaction with the virtualized GPU right here. Right. And now the question is, under all of these problems, what actually makes for reliable emulation? What do we actually care about? Here's a list of 3 things. It's kind of arbitrary, but, well, that's what it is. First thing is we want to avoid repetitive boilerplate, especially, for instance, for the system call interface. There's about 100 system calls on the system. And we don't want to do this kind of register reordering and value to type mapping for every single one of them, because we're bound to be doing it wrong at some point. We really want to automate all of this boilerplate by the compiler so that we just don't even run into danger of doing it wrong. We want to validate inputs where possible. If somebody is passing in an invalid handle into an operating system call, we want to catch that condition, and we want to catch it consistently. So if somebody is doing some behavior like that, we might be returning an error code. We don't want to return a different error code for one function than from the other. So we want to do it consistently so that we have a well-behaved system. And finally, we want to detect invalid system states, such as when the user passes in for instance, a file handle into something that is expected to be a mutex. That just doesn't make any sense. And it suggests that something went wrong in emulation earlier on that caused this handle to be incorrectly typed. Right, and today's goal is basically let the compiler deal with it and to see what the actual problem here is. I'll need to give you an overview of the Nintendo 3DS system first. So the Nintendo 3DS is Nintendo's current-ish handheld console. It was originally released in 2011. And there's still being titles produced for it, but it's kind of being phased out by the Nintendo Switch by now. It has relatively powerful hardware, so it boasts 2 ARM11 cores, has 128 megabytes of RAM, and it has a unique-ish GPU. At least it's not used in any other systems any other game consoles that I'm aware of. So it makes for a relatively interesting piece of hardware to emulate. It's also relatively powerful, so it's about comparable to smartphones at the time. And that is also reflected in the software stack. So this thing doesn't run bare metal software like predecessors like the Nintendo DS used to do. But instead, it's actually running a custom microkernel on the system that basically every of the game has to adhere to. So that takes care of things like memory management, multitasking, privilege management, things like that. And between the operating system and the game, there is actually a stack of services, that's what they call them, which are basically external system processes that provide certain functionality. We'll get there in a moment, actually. So if we look at this from the perspective of emulation again, we see at the very bottom we have the ARM11 CPUs, which we just emulate using a plain interpreter. So for those unaware, that's basically just a virtualized block of registers, just a C++ structure that contains 16 uint32 values. And we step through each of the instructions in a program and just replicate their behavior. So if we encounter an add instruction, for instance, we just take the corresponding registers, add them together, and store them back to the register block. And we do that for like the 200 or so instructions that there are, which are relevant for emulation. At the very top, we have the game and the browser. Well, mostly just the game, because nobody really emulates the browser, but you could. And what that does is basically we load the binary image into virtual memory, or rather into the emulated memory. We point our interpreter at it, and it just runs the thing. It's just as easy as that. Every now and then, that game will try to interact with the kernel. That's whenever we encounter a system call instruction. And we could emulate the kernel in a similar fashion. We just load the kernel binary to emulated memory, throw our CPU interpreter at it, and it would just work. It would be an immensely complicated and hard to debug system, but it would work. However, the interface between the game and the kernel is extremely well specified. Like, it's not a public documentation or anything, but we know how it works and it's not going to change anytime soon. So what we can instead do is some sort of API emulation, similar to what the Wine project does, for instance. So we just intercept those system calls and just defer them to a C++ function and then directly return to the game. And there's no kernel emulation in the stricter sense involved at all at that point. And it's similar with the system processes that are kind of between the game and the kernel. So they run on top of the kernel and have less privileges than the kernel, but they have more privileges than the browser and the game. So they can access the file system, for instance, or they can control power supply for the individual components in the system. And we use a similar approach for those. So we also emulate the interface between the game and those processes. However, it's worth noting that we could, if we wanted, emulate them in a more low-level fashion. Right. So to give you an idea of how this whole process or services business works, the idea is basically Nintendo wanted to give a game as little privileges as possible. So whenever the game wants to do anything interesting, it needs to talk to an external process which is capable of only doing a very limited subset of operations. So if they want to render graphics, it might talk to one process. If it wants to play audio, it might talk to a different process. If we want to access Wi-Fi, again, a different process, connect to friends, and loading assets and saving progress. The idea is being that if an attacker were to compromise the system, or rather compromise an application which only has access to, say, Wi-Fi and graphics, well, that attacker wouldn't be able to do anything interesting because they still don't have any access to the file system. Right, and others. So yeah, those are just the process names. There are about 40 of these processes in total, each of which is running simultaneously in a system. Usually they're inactive, but as soon as the game talks to them, they become active, of course. Right, so if we want to talk to a process, that's called interprocess communication. And as the previous slide suggested, that's required to do virtually anything useful. There is a quite standardized protocol between for this kind of communication. So it's client-server based, the game being a client and the services being the servers. And it relies on a request-response kind of scheme. So whenever the game wants to communicate with the thing, it just creates a request block, sends that to the service, and the service sends a reply back. And when more communication is wished to be had, they just send another request and get another response. And it's worth noting that this kind of communication doesn't... Oh, it's great. It's not like they talk directly to each other, but actually the kernel is sitting in between the two. That is necessary because sometimes they need to exchange sensitive data. Like, for instance, the game might try to, or rather the service might try to send the game 100 bytes out of a pre-allocated buffer of 1,000 bytes. And the operating system kernel can't just expose raw pointers of these kind of things because of how virtual memory works. Basically, the game would get access to the entire page of memory that the 100 bytes reside in. And then you could get information leakage and obtain information that you shouldn't be able to access. So that's a quite interesting system. And it's also noting that this kind of stuff is hierarchical. So the game might be communicating with the config service, but the config service might relay that the interprocess communication request to another service, like the file system service. And the file system service, in turn, might relay to the low-level file system service, PXI. So that's quite interesting to know that you just send off one IPC request and it just triggers an entire cascade of these kind of things. So, but it also illustrates that because this thing happens so often, it's quite important that we get it right and consistent. Right, so how does this look like in practice, actually? This is one example block of the application trying to trigger a read file operation. What we do is basically we have a block of 8 uint32 values in here, starting with a command header. The command header basically contains 3 pieces of information. The first one being a kind of index The index tells us what kind of operation should be triggered. In this case, 802 tells us it's a read file operation as opposed to opening a file or writing a file. The third byte, the last byte right here, tells us how large the first section right here is. This section is called the normal parameter block because it's just a plain list of values, so to speak. The other byte in here in the middle, that one tells us how large the special parameter block is. The difference is that the special parameters need some sort of translation process by the kernel, which we'll see in a second. So when this request happens, the application sends it off, the kernel will allocate an internal command buffer for this stuff. And we'll start copying around data, starting with the command header. And then it will copy the normal parameter block verbatimly into the internal command buffer. And for the translate parameters, it will do something interesting. It will translate these kind of things around. And how specifically it translates them around is specific to the particular block or particular parameter in question. So this one might be a buffer address, for instance, for the output data to store the read file data in. And since the service and the application have different virtual memory spaces, well, this one needs to be remapped into the virtual memory of the target process. So it obviously needs to be translated to a different virtual memory address. But once this kind of translation process is complete, the kernel will just send the data off to the service, where the service will kind of go through that block and decide what to do. And this is basically where our emulation core comes into play, because the emulation core is responsible for actually implementing this read file operation. And once we're done on the emulator side, well, what the services do, it will craft a response block, which adheres to the same principles. So we have a response header, and in this case, we only get, well, this is a typo, this should be a 3. 3 normal parameters and no special parameters, because it just reports back how many bytes have been read, in this case 0x100. And yeah, that's pretty much it. It sends that one to the kernel as well, and it goes through the same translation process. And then it gets sent back to the application, and then the application can inspect the result. What's worth noting here is that the first entry in here, that's standardized. It's always the kind of result code of the operation, and in this case 0 would signal success of the operation. Right. So the question though is, like, this emulation part is kind of the main problem that we have, and what's actually involved in processing this emulation part now? Well, basically it's a 5-step dispatch flow that we want to do here. The beginning is we want to select a kind of handler function to handle the operation. In this case, we just might have a do-read file function right here that takes a number of parameters. So they're well-typed as opposed to the command buffer. We might have a plain uint32, but also a 64-bit value and a more well-typed buffer, what's it called? Buffer pointer writable, yeah. Yeah. And when it wants to return data, we can basically return multiple values from that function using sttuple. So we basically return a result code and the number of bytes read in that case. Once we have selected the appropriate handler based on the command index, we want to verify that the command header actually indicates that the correct number of parameters is passed in. So we want to make sure that in this case we have 5 normal parameters corresponding to the 5 uint32 values we need to initialize these 3 values in here. So this one obviously needs 1 parameter, but a 64-bit value needs 2 32-bit values to be constructed, which seems reasonable, I hope. So together we have 1 plus 2 plus 2 equals 5 parameters, so we need to make sure the command header indicates that particular number of normal parameters. This one right here is a special parameter, so we need to make sure that we get two uint32 values in the command block from that. First one being for a kind of descriptor that tells us things like, is it writable, is it readable? Second one for the actual address. So that's another thing to ensure here. The third step is to actually read the parameters from the parameter block. So as an example, this is kind of a different structure of the same command block, but in the beginning, again, we have the header and the uint32 file. But then these two kind of go together because they are supposed to form a single uint64 value. Similar for those two, and then right here we have the buffer descriptor value. So we need to write some sort of logic that goes through this buffer and properly stitches the things together and constructs the right types out of it. And finally, once we've done all of that, we want to invoke the handler that we've originally chosen above. So that's just the C++ function call, basically, just that we somehow need to get our decoded value into the parameter list of this function. Right, and this one will return the stattuple above here, and we want to encode that back into the response command block so that the game actually knows, what the hell is going on. And because this process is kind of the central element of my talk, or rather automating it as the central element, I've decided to give it a funky name. More so because I need to reference this process 20 slides from now, and I need to make sure that 20 slides from now you still know what I'm talking about. So I like to call this svpeer. Very catchy, I know, but that's what it is. So right, the question now is this actually worth automating? If we just need it 2 times, why bother doing that? But turns out, if you think about it, we have 40 active processes on the system as illustrated by before, and each of them has 30-ish IPC commands on average. There are worse offenders. One example is the file system module. You can actually look at this kind of stuff at the 3D Wiki, where most of the information about this kind of stuff resides. And there is a section somewhere here about, there we go, about the actual service commands. And you can see like each entry in this table is one IPC command. And well, let's just say there are a lot of them. Now imagine you had to write this svpeer process, dispatch flow for every single one of these. You'd basically go insane at that point. So yeah, each of those have that, and each of them in theory requires manual C++ glue to actually get hooked up properly to the handler function. So yeah, that's a lot of work. It's even more work if you consider we need to do it correct, we need to do it consistently, and well, at the end of the day, we want to have a solution that's actually maintainable and doesn't require a day of work or so if we just do a tiny change to the interface or something. So yeah, we'll see how declarative and generative programming help us actually address this kind of issue, starting with declarative programming. Just wondering how many in the room actually have any idea, like just a vague idea of what declarative programming is about? That's a couple of hands, okay. So if you want to summarize it as concisely as possible, it's basically about about separating the what from the how. So what we want to do is we want to take a step back. We have this very ambitious plan of emulating 3DS services, fully automated, and it just works. But maybe we need to take a step back and just focus on describing the kind of things that we actually want to emulate here. And once we have a description, maybe we can focus on the actual solution later. So let's do just that. To describe the IPC commands, well, let's think about what is the actual information required to describe a single command. Well, the first thing is the command ID, which identifies, are we reading a file, are we opening a file, are we getting its file size? Second one is the kind of list of normal parameters that we are reading. So for a like, is it just a plain uint32, or do we need to stitch together 2 values into a 64-bit value? These kind of things. Do we maybe need to map the uint32 to an enum type? And then the list of special parameters that need to have this descriptor value and also need a similar stitching together. And finally, the same two lists again for the response data. So it's another two lists. An example for open file, command IE might be 0x802. It might get a uint32 at the very end, but also any enum IO flags and file attributes, something like that. And for the request data, I just get some sort of static buffer, which is one of the special types that I'm using internally in my project. And yeah, the response data is just a file descriptor, again, just a plain uint32 and no special parameters. The essence of that is what I want to do is I want to capture all of this information at compile time. This is important because what we want to ensure is that as soon as we do something incorrect in our program, we want to get a compile time failure about it. We don't want to realize just at runtime, like when we run our tests, or worse yet, when the user has already sent a bug report. We don't want to notice at that point that we did something wrong, but we want to notice at building that this cannot possibly work. So this is basically the reason why we need to encode this kind of information, for instance, at the type system level. And I will show you the one possible approach of how you can encode this right now, but I will omit implementation details to the next slide. But just to give you an idea of how this might look in practice. So just a namespace around here to group things. We might start with a using declaration. So we want to encode things at the type system level, so we logically need to have some sort of type. And the interface I came up with here is called IPC Command. It just takes a single template parameter, and that is the command index. And you can imagine that this type just does nothing but expose this command index to its users. So it just has a single member called static const expr auto this value. But that's of course not all the information we want. We want to have the normal information list. I do this by having a subtype in the structure, which is another template that gets the list of actual template parameters. This one in turn has another substructure called special, which captures all the list of special parameters. And then similarly, we have a response subtype that does something like this. So this is probably a somewhat unusual way of declaring things. Possibly you have no idea like what the hell is going on in here. But hopefully you agree that if you understand how this IPC mechanism works and you look at this code, well, you basically immediately know what's going on. Because you know, okay, yeah, of course, there's the command ID, takes these normal parameters. It's obvious. Like you might not understand how it works, but you will understand what it says. And that's a key strength of these kind of declarative interfaces. And yeah, you could do the same thing for all the other IPC commands like get file size. It just also has the same very structure and just captures all the information we need in a very minimal interface. How might you actually implement? Right, yeah, worth mentioning, this is a builder-like pattern, if you ever used the OOP pattern. But yeah, how might you actually implement it? Well, let's just start with the actual main template. It's just a template structure, taking a single parameter. There's nothing special about that, it just works like that. But the question is, how do you actually export the properties again? Like, we want to do anything useful with them? Well, you just add a member static const expr command ID equals the given template parameter. It's really easy. If you want to tag on the normal information, you need a substructure in here. Well, you don't need it, but that's how I designed this interface, because it's just the easiest way to specify this information. So you have the subtype struct normal, and it just re-exports the normal parameter list as a tuple, like this. And then you can just tag that one. And if you want to keep going, you add more and more substructures to the thing. Right. And you could do the same for the response data, but this is omitted because you can imagine this thing just kind of gets complicated. But the key point is this is all you really would expose to your library users. Like all of this stuff above here, that would just be an implementation detail, so to speak. If your stuff works, you don't really need to look at it, which is a good thing. Right. Right, and the key here is basically that we kind of have a mapping between these declarative interfaces, these types, and the tuples inside. So if you want to actually get from this type definition the actual parameter list, well, you just use open file : normal params, and you will get the thing. Right. So the idea about declarative compile time program is basically we have a number of building blocks. It looks like this. This is kind of a graphic I like to show with these kind of things. The declarative interface is the base starting point for when we want to do our thing. And we basically extract the tuples contained in them, do some sort of template metaprogramming magic on them if we, for instance, want to do things like convert an element to a pointer type, etc., things like that. And then we want to use a notion I call generators to convert each of the elements into some sort of runtime code. So you can maybe see where this is going, where I want to iterate over the type lists, over the normal parameters, for instance, and generate some logic that parses each of the elements from the command buffer. And you can use this using different kinds of declarative interfaces. The one I've shown you before is just one example of type-based systems. You might just have a plain type list as well, or you might go full-blown by using domain-specific languages or expression templates. You might also use things like const explorer objects. For instance, I'm using const explorer lookup tables in a different project to automatically generate virtual memory mappings. You might use reflection-based systems, like where you actually generate the type lists directly from the C++ entities you're working with. An example might actually be my C++ London talk, where I automatically extract the type lists from function parameters, which is possible today, and hopefully it will actually get more powerful with C++ 2b or something. Is there some way to go? And yeah, there's a distinction to be made between plain definitions and sort of embedded domain-specific languages that use operator overloading and things like that. Right. So the vision I would kind of like to go through to address our SVPeer problem is we have the high-level C++ handler and the declarative interface. Well, what we want to do is we want to extract the response lists from these declarative interfaces. And then we have this notion of generators that on the one hand take these tuples, and on the other hand they take this command handler. And they kind of stitch the two together and make sure that we generate the corresponding logic to decode all of the parameters from the command block and automatically call the C++ handler with that. And at the end of the day, we will actually combine these things together to get a single function that I call glue command handler, I believe. Yeah, glue command handler. It just takes the IPC, like declarative interface, the command block, and the C++ handler, and it will take care of the entire SVPeer process for us. So that's kind of a long-winded introduction of why we actually need all of this stuff, but I hope being able to reduce the SVPeer process to this single function call is sufficient motivation for you to see what I'm getting at. Right. So the advantage of this approach is we automate the entire process. We don't need to manually read things from the command block and stitch them together anymore, but it's just automated. The compiler generates all the logic automatically for us. It's type safe because, type safe by design, so to speak, because during this process we can make sure that the definition in the declarative interface actually matches the function signature. So say in this normal list in the declarative interface we were missing the UN64 value. Well, then the program wouldn't compile because this handler has a UN64 value in its function signature. So something must not be right, so rather than catching this error at runtime, we catch it at compile time. And finally, all of this is easier to read because there is nothing to read anymore, because the entire 5-step process is broken down to a single function call that is trivial to decipher. Right, so since I'm kind of running short of time, let's rush through this. Notion of generators is basically just we have these type lists, we want to turn it into runtime logic, like decoding and encoding and these things. So what we do for these, we have multiple means. In C++98, for instance, you would have used recursion techniques or maybe resorted to boost MPL or something like that. With C++11 and particularly 17, we have more powerful means to do so, like parameter pack expansions and fold expressions. So how does it actually work? Here's an example. Let's say we have this type list at the top for the request header. Hello? There's my mouse. There is my mouse. And the idea is basically for each of these types in here, we want to read the corresponding element from the command block. So for the first UN32, we want to read the first entry. For the UN64 right here, we want to stitch these two values together, etc., etc. So how you might want to do this is we want to, first of all, start at the simple problem, just decoding a single entry. So we might be tempted to have a function called decode entry that just takes an offset into the command block and the command block itself, and then reads an element of the given type. I will show an implementation of this later, but let's just assume for now that we have this already. And then we can write a function called decode all that is a variadic template, so it takes all of the types contained in here, and then it runs over the entire command block, and for instance, it could return a std tuple of all of them. And how we do that is we just initialize this offset variable, and then we use a parameter pack expansion. So we have our function decode entry. We pass in our current type at the current offset in the command block. Right, and then we expand the entire thing. So what the compiler will do in this case, it will basically take this expression and duplicate it for each of the given types. So it basically automatically iterates through the entire command block. Now, what I probably should have mentioned is that this function actually updates the offset in place. So this thing doesn't just read from the same offset over and over again, but it will read the first thing from offset 1, then it will move to the next one, and to the next one, and to the next one, and to the next one. Right. And as I was saying, what we could do now right here is we can return a std tuple of the read results. That's a perfectly legitimate solution. But what I have actually found more useful in practice is that I actually specify the handler directly to this template and then call that template, the function directly with the parameter pack expansion in here. So that's quite the neat trick in my opinion, because it's maybe not something you would do naively, but it just works, so why not? Right, so how does our decode entry function actually look like? If you think about how to do this with C++11, for instance, it gets quite messy actually, because we want to specialize this function on every single type, and sometimes depending on how many other template parameters you have, you basically need to employ sphenatrix to make this work. C++17 actually gives us a very powerful mean to do so, which is if_const_expr. So if_const_expr allows us to just check, is the current type a UN32? And if so, well, just read the UN32 from the current offset and then use post increment to increment the offset after. However, if it's a UN64-bit value instead, also read the first UN32 value at the current offset and increment it, but store that in a variable while low. Then do the same thing again to read the next entry, and then return the stitched together result of the two. It's worth noting, const_expr_if takes care of making sure that the return type is different. So in this branch, we would be returning a UN32 value, in this one, a UN64-bit value there. Right, and we can add more specialized branches for this. So we might have one for the writable buffer, which decodes the descriptor and creates, decodes the descriptor and then reads the address and then returns an object of the strongly typed writable buffer. Right, so that wasn't too bad, I hope. But you can easily see now, if you put the two together, you just easily get this solution that runs through the entire command block and applies the result to the function. Cool. No boilerplate anymore. The caveat is, however, that the interface that we want is actually somewhat different, because we don't have a template function that should be a variadic template, but the template argument itself should be a tuple type. But that's kind of a standard problem. What you can do in that case is you just turn the function into a structure with a function call operator, or with a call operator. The generic interface here just takes the type list, and this one is then a partial specialization of the thing. It's kind of ugly if you see that for the first time, but it's kind of standard, so meh, whatever. But if you want to learn more about these kind of things, I can recommend the talk Template Normal Programming by Arthur O'Dwyer from CppCon 2016, where he talks for 2 hours about, well, basically how to understand these kind of template metaprogramming tricks. It's really good talk, so I recommend it. The second caveat is the execution order of this thing is actually not well defined, unfortunately. So it will, it will duplicate this kind of thing multiple times for each entry, but it's not actually well defined. Like, does it evaluate the thing first for UN32, or does it evaluate the thing for the buffer address first? And that's, of course, terrible, because we want to enforce a strict execution order here because of the offset here. If you don't get the offset right, it will just blow up in your face. However, there's a quite easy workaround for that I found, which I'll be presenting tomorrow actually on Wednesday in the lightning talk session. So if you're curious about that and how to resolve it, I think that I called the talk curly function call syntax. So yeah. And that is a good point to actually show a quick demo of things. We're really running short of time, but I hope I can show off the main elements of this thing really quick. Right. So is this readable in the last row? Lovely. So I'm basically just setting up a kind of dummy environment here with all the types we've already seen. And here is the decode all and apply template we've seen before with the decode entry function as well. It doesn't really look any different from what I showed you on the slides. But the thing that's different is that we have this do stuff function here. So just a similar function to what we've seen before, and it just prints out the values directly via std out. And then main function, we have a command block with the raw values, and then we just use the decode all and apply. Where's my mouse actually? I don't see it. Use the decode all and apply template to automatically decode the command block and call the function handler. So if we try to compile this, which actually works apparently, we see, it just prints hello world in the beginning of the function and prints the first entry and then the stitched together UN64 value and this writable buffer value. So it just works, which is nice. Cool. Running shorter on time even. The one thing I did mean to show you, of course, was the encoding part as well. That's mostly the same thing, although it's slightly different in that we don't want to forward the decoded results to any function, but rather we just want to execute the same statement over each of the type list elements. The way you do that, so we have, again, an encode entry function, and we call that on each of the type list elements, and then it iterates through the buffer. And you can repeat over that by using the comma operator and a fold expression. So what the compiler will do in this case, again, it will duplicate this expression multiple times, but then it uses the comma operator to call one after the other. So in that case, it's actually better than before, because this one enforces a strict execution order, which is what we want here. Right. And now the final piece of the puzzle is the glue command handler function. I'll just show the entire thing. Where, if you remember the SVP process, well, we just have it here on the entire slide, basically now. We read the command header and make sure that the request header is actually what's inside of the declarative interface. So this is a member I hadn't shown you before, but basically it's just another member of that declarative interface that you can easily compute. If it doesn't match, it just throws an exception or does any other error handling kind of technique that you prefer. It then decodes all of the results using the same line as that we've seen before. So it just takes the request list from the declarative interface and the command handler. Right, and after that it just writes back the response header and encodes the response into the command block. So that's really all there is. The point is, this can be used for all IPC commands. It's just a single template that we only write once. It's not even that complicated in the end, and it just works. But that brings me to the biggest plus actually of these declarative interfaces, because you write them once, and they're relatively simple to understand once you are used to the odd syntax. But the thing is, the handlers are only one possible backend of this entire thing. What you can actually do is you can repurpose these declarative interfaces to do entirely new things, like synthesis of command blocks, which I'm actually using for the low-level emulated variant of these services. So it's just possible to write a function called craft block that takes the declarative interface and automatically fills in all the parameters into the command block for you. And similarly, you could do some sort of logging backend for your system where you automatically compare this kind of command header to an internal database and then realize, automatically detect basically what this command block represents. So for that, I also have a quick demo, and then we're basically done at that point. Right. Yeah. So we have similar boilerplate at the top, but here we actually have the declarative interfaces in now. They look slightly different, but it's mostly the same thing. We have a similar decode all and apply function again. There's an encode all thing. We have here the glue command handler function, which was the first kind of backend. We here have a craft command block function, which I unfortunately can't get into detail right now due to time constraints. But you can see it's also not all that complicated. And then finally we have the, where does it actually start? Right, the detect and log command, which looks at the command block and compares it against an internal IPC command database. So the IPC command database is basically just a list of all the elements we declared at the top and maps them to individual names. So you can see that it compares the command headers against the internal database and then automatically prints it out. Right. Yeah, then the main function, we're doing a lot of things, but we actually don't need to look at that. Let's just look at the actual output of this program. Please? Yeah, that makes sense. Thanks. All right, good. So this is getting kind of complicated because I can't actually read their own thing, but oh well. So in the beginning, we seem to be creating a command block, which looks like this. The corresponding snippet in the main function is this one. So you just have this function called craft command block with the open file function, and you give it those parameters. And what this function does, it automatically encodes them in command block. The second line then inspects this command block. So this is totally artificial, by the way, but it compares against the internal database, and it detects, hey, this is an open file command based on the command ID up here, and it rereads the parameters out of it. The next one actually glues this one into a handler function that I called doOpenFile. Actually skipped a couple of things here unintentionally. There we go. And that one just prints called doOpenFile. And then we do the same again, basically with a different thing called read file. So it just again creates a different kind of command block, runs the command database over it, detects it's a read file command, and then calls the read file handler. And then for the sake of it, I just tried detect and log command on a dummy command block that contained garbage data, and it would say unknown IPC command. So that's quite neat in my opinion. You basically just have these centralized definitions up here, and you can do all kinds of different things with them just because they have a centralized definition for them. Right, so to summarize very quickly, what is all of this that I just showed you good for? Well, it separates contents, what versus how, which is really good because rarely you have a difference, a change in your system where both the structure and the logic of your system change. So it makes logical sense to actually separate them. It's good that you can actually bring up entire features really, really quickly because you can refer back to these definitions that you already have, if you wanted to have a logging backend. I kind of wrote this on the plane right here in like 2 hours or so. And it was actually working perfectly after, so it was really, really quick for what it is. You can express the programmer intent much better than you can do with the manual boilerplate all over the place. It encourages automation in the first place because automation is really the only place you can actually do anything reasonable with these things. And it helps detect errors at compile time, again, because of this enforced genericity, for instance. Right, so to summarize, it's a improved flexibility, time to market, and maintainability benefit for all of this. Conclusion. Serialization is a centric problem in emulation, and hopefully, or for you, maybe also a problem if you're dealing with any kind of communication problem at all. We can use these kind of generators to automate most of this functionality, and declarative interfaces play a central role in here. And it's a kind of not novel thing in the sense that that I invented it or something, but it hasn't really reached the mainstream quite yet. And maybe with this talk you've seen what kind of potential it has and how you might be using it in your application. And yeah, in summary, it's vastly more maintainable and expressive at zero overhead, which I didn't show actually, but if you looked at the assembly generated by any of these things, you will see it beautifully optimized by the compiler and just basically generates generates code that is equivalent to handwritten code at that point. Right. And with that, I would like to thank you for your attention. And if you've got any questions, feel free to come up after and we can just talk in private about that. Thanks.